All right, everyone. Good morning. Let's get into it. Obviously, this room is marginally better than that room. Unfortunately, this is as good as we could get. The whiteboard does continue under that, so we'll just have to put screen up, put screen down as we go. But hopefully, I'll try and limit my writing to about that so that no one misses anything. If you are missing something, if I write too far, just tell me, because I might get carried away. Now, all right, so last week and the tutorial yesterday, we did forces, shear force, bending moment, etc. That's basically as much as I'm going to devote to reviewing that with you. Everything we do from here on in, you'll have to do that again. So obviously in tutorials and things, I'll be available to help you through that part as well as the subsequent bits that we do. Most of you will have seen that I've put up the solutions to two extra, slightly more complicated problems under, I think, yesterday's tutorial folder. They come from the back of the textbook, so all of Chapter 2 reviews exactly what we've reviewed. And all of the problems in the back of Chapter 2, and there's some 60, 70 odd of them, do force, some of the forces, shear force diagrams, bending moment diagrams, and so forth. All right, so there is just so many different examples that you guys can have a crack at if you're feeling uncomfortable with it, or if you want to refresh over the next couple of days. For two of them, as I said, I put the full work solutions up online for you as well. All right, so please make sure that you're completely across this stuff. This from here on in is assumed knowledge. All right, so if you get it wrong, then you're going to carry a lot of errors through a lot of other stuff. So make sure you're across it. I'm always available to help you through if there's still something that's a little bit niggling and that you don't get. But otherwise, this week, we're going to move on to, so that was that part. This week, we're going to move on to stress and critical zone calculations. Now, I'm going to assume that you've done that in CS 2001 as well. And so what we're going to do is a refresh and start to get slightly more advanced than you've probably seen. And given how frequently we use it, it's very worthwhile to always have a refresher before you get into something. All right, and I mean, the major reason that we're looking for critical zones or calculating stress in the first place is stress is what causes failure. All right, high stress is what causes failure, or stress is a measurement of the amount of force being distributed over a couple of, however many atoms, and certain amount of force will spread those atoms further than what their bonds can hold, and as soon as the atoms separate, they don't, join back together. That's called failure. So at an atomic level, you're just talking about atoms coming apart. At a larger level, that becomes a crack, and as soon as you have a crack, that then becomes a proper failure and things start breaking and spitting pistons out of engines and so forth. So what we're interested in is avoiding that. The way that we determine that is stress, because if you know the stress and you know what stress something will fail at, then you can compare to that and make sure that you're under that. Now the stress for a machine component will be potentially different throughout the entire cross-section of the machine component, as you might imagine. It's largely force density, so the force might be more densely carried by a certain part of the machine and less densely carried by a different part. So looking at this example, this is an example from finite elements. So the reason we do finite elements and the reason that you're going to do it in EG 3001 is that instead of just calculating one critical element and running the sums on it like you're going to do in this class, or maybe 2 or 3 potentials, you effectively have critical elements for every single piece of that material, and the computer calculates what we're going to calculate. What we're going to calculate for a couple of elements, the computer calculates for every single element, and you know what the stress is everywhere. And then you use something like this, a contour plot, where red means high, blue means low, and you can visually see where the critical area is. And from this, we can see that this is critical here at the corner. And so that might, as it rotates, might cause a crack to come in here, and then the machine the large roller to actually shear off. All right. And so understanding where that critical zone is, FEA is very good for complex stuff, but we're going to be able to do that for the more simple shafts, beams, bars, that kind of stuff. The bread and butter things, bolts, welds, gears, all of that sort of stuff, we can analyse by hand, and we have a good understanding of where the critical zone is actually going to occur. All right.
Sorry, Dave, is that a bolt?
That is actually I think that's part of a larger roller. So that's the shaft of a large roller, I think. And that's a section there. Yeah, this came from a previous lecture slide where that roller was actually, I think it's about that diameter from memory. And that roller was actually fatiguing at exactly that point and causing slow fatigue cracks coming down like that. That's a cross section. That's a cross section, yeah. That's half, and it's half this way as well. And so by working out where the critical zone is, they worked out that this particular force was sufficient to cause that fatigue failure and that it wasn't analysed correctly in the first place. And so that's a lot of the root cause analysis type stuff that I might talk about. Generally happens when something breaks and you go back and look at the design documents and work out what forces they actually used for their calculations, and then you work out what forces something's actually operating at. And maybe it got designed 30 years ago and you're dealing with plant machinery that, you know, you've upped production by 200% since it got designed, and now it's working outside of the bounds of the assumptions and things that were made in the initial analysis. So root cause analysis is a big thing, particularly when things break, and then you've got to redesign things to avoid that in the future. All right, so the main types of stress, as you will be well aware, are axial, torsional, bending, transverse shear, direct shear. So that's on a specific shear plane rather than transverse shear, so that's slightly different. We'll talk a little bit about that. Largely direct shear just means that these two levers, I suppose, means that shear is only going to occur on that plane, whereas something like transverse shear occurs throughout the entire cross section. Okay, so it's slightly different. It's kind of localization of that shear stress. And you've probably analysed these separately. Have you analysed any of these in combinations? Hands up, yes? No? So hands up if you've analysed all of these separately. What haven't you done the most? Sorry? Transverse shear, not too much transverse shear. Okay, good. That's what I need to know, because I don't need to know how much depth I go into it. All right, so what we're going to do is we're going to talk about each of these individually, and then we're going to combine them. So what happens if you have a transverse shear and a bending moment and a torque all simultaneously, and where's the critical stress, and how do you combine those stress elements? And fundamentally, we just add them. So they're just, you know, you calculate the stress elements separately, and then you combine them all, and all the vectors add or subtract or whatever, and then you have a 3D stress state. And then you need to combine that into something, be it a principal stress or a von Mises or something, and I'll teach you that as well. So we're going to start simple, which is talking about each of these individually. Hopefully you've at least seen that, and then we'll talk about combining them probably in tomorrow's lecture. All right, so axial force is the easiest one. Now, when we're talking about calculating stress, we've got kind of half the story from our diagrams that we've been doing. So our shear force, bending moment, etc. When we're talking about a beam or a shaft or a bar or a member or a bolt or something like that, and we've got some sort of a length over which we're calculating, these diagrams give us the actual value of force throughout that entire length. Very useful, all right? So we just go to the maximum point of that, and that'll be the maximum force, and chances are if we've only got one mode of loading, that's where our critical point will be. But that's not the whole story, because as we know, stress occurs differently throughout cross sections depending on what that stress is. Now, axial stress is very easy. If we look at the cross section throughout an axially loaded member, then it's just perfectly evenly distributed. It's a nice, flat, even distribution of that stress. So if I was to take an element at this corner or an element at this corner or back 2 corners or anywhere in the middle, the stress element would look identical. All right, so infinitesimal element, we're talking, you know, theoretically atom dimensions, but, you know, we draw it however it is, you know, whatever size is easy to draw. But it's assuming that it's a point in space, not an actual volume when we draw one of those elements. And if I drew one anywhere on that surface, it would look exactly the same. It would look, you know, you'd have a box and an arrow up and an arrow down, and that will be an axial load because our load is evenly distributed. And so this is what that looks like, the way that I want you to draw it. Everyone remember the isometric drawing that we talked about in EG 1000? That stuff actually comes home to roost right now. So when we draw these things, we need to be super confident and comfortable either drawing ISO or the oblique, remember, with the, you know, square front 45 degrees back. because when I draw this and I draw these four little elements, I oftentimes want to blow that out, because by the time I add vectors and numbers and stress symbols and things to it, that's going to be too small and it's going to be really complicated. And you want to be really consistent with the way that you draw it. Right? You can see, if you look at my drawing here, it's very clear to me that these are the same elements as those. And I'm not going to confuse a front face with a side face or a top face when I'm adding those vectors. All right? If you, for example, if you were to draw a beam like this and say, all right, I've got a stress element here and one here and one here, and then you change your aspect and you start drawing them like this, one here, one over here, one down here, something like that. And I see it time and time again, so I'm exaggerating this, but the front face here, which face is that here? Yeah? So it gets really confusing really quick if you're not consistent and you keep those axes on the same plane. So that's one little statement that I'll say right from the very beginning. When you're drawing these things, right from the beginning, try and concentrate on your axes. And if you need to go and buy some isometric or print some isometric graph paper out or something and use that for your problems, feel free. But you should be able to keep a fairly, 30-30 straight up and down. Keep a fairly good, consistent drawing if you try hard enough and you practice it, right? So that's the first thing I'll say. This is our easy problem. This is our axial problem. We've got P and P, and it's even throughout the entire length. It's even throughout the entire cross-section. So I can draw a box literally anywhere in that, and I should have exactly the same sigma, sigma going along that axis, and the value of sigma is just P on A being the cross-sectional area of that particular item. Now, is that different if it's a circular cross-section? No, identical. What about if it's an I-beam? Identical, doesn't matter. Axial load, so long as it's, not unevenly distributed. If you apply it through a bolt hole or something, you might have some sort of a different curve, but if it's assumed to be evenly distributed on each end, doesn't matter the cross-section, wherever the element you find within it will have even stress, sigma equals P divided by A. Cool? That's the easy one. All right, now the reason this is important is because this won't tell you where the critical zone is. All right, the critical zone for an axial load is everywhere. If we then added an axial load to a bending load, then the bending is going to be different throughout the cross-section, and you need to work out where the bending and the axial add and where they subtract, and that will tell you where the maximum is. So we'll talk about that more. This one's easy because it just tells us that anywhere I put an element, it'll be the same. Now, torsional loading. Some people during tutorial were talking a little bit about the difference between using a double-headed arrow to indicate torque as opposed to sort of one of those loopy kind of arrows. I really like using double-headed arrows for torque because when you're drawing it on a 3D diagram, and particularly when you translate that 3D to a 2D space, if I was to draw that on this 2D space, it's sort of, you're drawing a bit of a loopy thing. It doesn't look really, right. And if you've only got a torque, maybe it makes sense to you. But if you have a torque on that end and then you have a moment on that end and you have a different moment on that end, you've got all these loopy arrows everywhere and it doesn't, it makes it really difficult to interpret your drawing. So as soon as you turn it into one of those arrows, right-hand rule, arrow points in the direction of your thumb, you know which way it turns. It's really easy to interpret on a drawing. So that's why I prefer those for torque. Now I have three separate examples of shafts that have torques applied to them. This should be fairly simple for you guys to work out what the torque diagram might look like. It's exactly the same as, say, an axial diagram or a shear force diagram in terms of, starts positive, ends negative, that sort of thing. This very simple one, we've got a wall and we've got a torque. That's obviously not a free body diagram because it's moving in space, or it's, it's not free. And then if it were free, it would be moving in space because I don't have all my forces resolved on that. Hence, I draw my free body diagram. Torque goes on, torque goes off, nice and even. We look at our positive sign convention and we have positive torque everywhere, and so that's constant over the entire length. All right, so if I was to calculate a stress element anywhere throughout the entire length, T would be the same. But we know, and as I'll talk in a second, throughout the cross-section, torque isn't consistent throughout a cross-section. So all I know now is T for the entire length, and now I've got to think about the cross-section in a minute. For this example, I've got a pulley in the centre, and nothing attached to this end, so there's no way I can get any reaction forces on this end. Obviously, it's attached to the wall, and that's the way I designate walls. You also see walls sort of like that, you know, whatever. If it's unclear, feel free to ask. If it's an exam and it's unclear, feel free to ask. You know, I'll tell you. It's not a problem. And so obviously that's the reaction torque. And this starts to get why I want you to do torque diagrams as well. Torque diagrams are trivial. They're pretty much arbitrary, except when you have a circumstance like this, where that half of the bar doesn't have any torque on it. Okay, so the torque diagram tells you, if you do the torque diagram correctly, so take our little section there, we've got positive torque that way until we get to that point, and if I took a section just to the right of that, my sum of the torques is this one that way, and nothing left. Okay, so obviously it goes to 0 to the the right-hand side of that bar. So on the torque diagram, we indicate that as 0. Now, that's important because a lot of the time, the entire length of that bar might have transverse shear and the entire length of that bar might have bending, but only some parts of it might have torque. And so you might have sections where you have less bending, but that bending might add to torque, and sections where you have more bending, but no torque. I'll say that again. So if this had bending on it like this, you might have less bending there, but that bending might add to the torque and be more critical than over here, where you might have maximum bending, but no torque. And so we need to be very careful about where we do and don't have a particular mode of loading, because when we add them together, you know, two small ones might add up to more than one large one. And we need to be very conscious of that. So that's why I want you to do the torque diagram and be very, very careful about where there is and isn't torque throughout a particular member. This is another example of that. If I have some, you know, bearings at each end and then a couple of pulleys or something, gears in the center there, then we're looking at nothing, and then torque applied, torque throughout this section, torque taken off, and nothing again. Right, so the torque is only between the two applications, or the, you know, the balancing applications of torque. And so our torque diagram might look like nothing, nothing, nothing. This one's negative, looking at our torques, they go in, and then nothing again. Okay? So the reason we do the torque diagram and we put it directly under the bending moment diagram, the shear force diagram and everything, is when we look at a section, we can tell exactly what the combined forces are for a particular section, and then we calculate our stresses as a result of it. Okay? Now, torque. Everyone familiar with torque? Everyone know what the cross-section of torsional stress resulting from torque looks like? Yes? No? Okay. So, if I have a torque T, and remember we're reading torque off this diagram, so whatever value of T I calculate at that diagram at maximum, that's T. And our torsional stress, our maximum torsional stress, or technically this is the value of torsional stress anywhere throughout the cross-section, is T R on J, J being the polar moment of inertia and R being the distance from the centre. So if my distance from the centre is 0, what's my torsional stress? 0. So torsional stress at the very centre of some sort of this, let's say, circular cross-section, or at the neutral axis of any cross-section, torsional stress is 0. And as I go up like this, R increases linearly, and so the torsional stress increases linearly based on this equation. And where does the maximum torsional stress occur? Yeah, at the maximum value of R, which happens to be, for a circular cross-section, at the outside surface. All right? So if I was interested in what is the most critical stress element when we're talking cross-section for torsion, I would choose something on the outer edges. All right? And that could be arbitrarily the top. It could be top, bottom, left and right. It could be, you know, wherever you want. And oftentimes the place that you choose those candidate elements will be sort of indicated by other stresses as well. So if we have bending stress, we know that's maximum at the top and bottom. So you might have a top and bottom element of torsional stress as well, because you want to know what they add up to there, you know, that kind of thing. But again, I'll talk about it. So TR on J. Now J for a circular cross section is this. You've got J for rectangular cross sections and any other number of things in your textbook. You can also look it up online, and there's also ways that you can actually calculate it yourself. So you can actually derive J if you want to. It's not as important for beams because it's pretty, well, you know, these type of cross sections, because it's pretty easy to find a value for it online. But for welds, it's very useful to learn how to calculate J's and I's. And so I'll talk briefly about that when we talk about welding. But this is the one for circular cross sections. Now, I have a rectangular cross section. And I'm applying a torque to it. Where's the maximum stress? Sorry? Corners? Yeah, so neutral axis is going to be basically in the very center of that cross section, like so. And based on that equation still holds, aside from the fact that I use a different value for J. R is longer there than it is there. So wherever my longest R is, that will be the maximum torsional stress. Okay, so in this circumstance, that's at the outer corners there. So any sort of beam, I-beam, anything like that, you can always have torsion on it. It's just where's the maximum R, use that equation, that's the maximum stress, and that's where you would want your candidate stress element. Alright, so easy enough. We get T, we work out our maximum T from these ones. We have an understanding of what that equation means and an understanding of what torsion looks like throughout a cross section based on what I've just been talking about. And so we can then come up with candidate stress elements and draw our stresses on them. So for the third example from what I showed, that's the, the bottom example there. Somewhere in this section where I've shaded that outer surface, because we know the outer surface is maximum, and in that central section where T is even, anywhere in that surface, we know that our torsional stress is maximum. And just to calculate it, what we might do is do 4 stress elements like that then would add to 4 stress elements from whatever other forces that we have. Now, an interesting little exercise. There's some rounds out here. You guys probably have a pretty good grasp of that. You might not have a grasp of is the direction that those vectors go in. Just sort of have two each and sort of share and look on. Got some rectangular ones too, that's not going to really serve much of a purpose. So you want 2 of these. I'm doing this not because I think you guys are kindergartners, but because what we need to develop is a nice 3-dimensional sense in your minds. In the absence of, Alright, so we need to be able to work out what direction our shear vectors go in based on torsional stress. Now, some of you might have a pretty good grasp of that, some of you might not. And I saw in the tutorial yesterday a lot of people using their right hand rule and waving hands in the air. I love that. That's perfect. Do that as often as humanly possible because that tells me you're thinking about 3D space. All right, so you need an idea of 3D space in your mind to be able to get this stuff right. Now, the reason I have these is that hold those 2 up and join them together. All right? Now, joining them together, that section that we've just cut off, let's say our front face of these cubes, that's the section between the 2 cylinders that you have. And the way that we determine the direction of those vectors is, everyone's seen, that sort of a velvet type fabric where you run your hand one way and all the fibers stand down that way. You run your hand the other way, all the fibers stand down the other way. All right? Imagine that we have that type of fabric on either face in that section, okay? And now what you're going to do is get your hands either side and look at the direction of my torque that way, and I'm going to rotate my hand that way, and look at the direction of the torque that way. I'm going to rotate that way. I'm going to give my my cylinders a Chinese burn, I guess, if we think of it that way. Now think about that front face, and this hand is holding the one that has the front face I'm interested in. and think about what direction those fibres are going to go in that fabric. So as I rotate it, they're all going to sit down that way, aren't they? As you rotate that, it's going to push down the fibres and it's going to push it down all the way around, and they're going to go that way. That's the direction of your stress vectors. Right, so as you rotate those things, if it's rotating that way, they're going to be sitting down this way, this way, this way, this way, and all point round in a circle. And if you think about it, think about the opposite face. As you rotate it round, they're sitting down in the opposite direction. And remember what we said about internal forces? The same thing applies for internal stresses. When you glue them together, they cancel out. They have to be going in opposite directions. All right? And so by visualising it, and I don't care if you use blocks, I don't care if you use your mind, you can just as easily use your fists, and you can put a dot of ink on your knuckle and smudge it. And the direction of the smudge goes around, and that'll tell you which direction the vectors go. It doesn't matter, but that's how shear actually works physically. That's what shear stress is. The shear stress is pushing that front face over and shearing it across and causing stress that way. And so the direction of the vectors has to mirror that. It has to represent the direction that the front face of that material is being bent over. Right? And so once we have the front face, we can get the other four faces that complement it, because we know that shear force or shear stress always points towards the same edge. So if I've got my front face there, I know the side face there points to that edge. I know the back face points in the opposite direction to that, because they have to have their tails at the same time. And just think about that back face for a second. Excuse me, that's pointed that way now, which is exactly the same as the other opposite face of the one you were holding in your other hand as well. So we know full well that that's going to be that way. If we analyse that section using our visual means, we would have got that. If we analyse our section using what we know about shear vectors all pointing to the same edge, we get the same solution.
So is that the internal reaction forces, or is that just the external torque?
Well, that's the internal shear stress. Okay, so what we're calculating now is the stresses. So we did forces yesterday and before. The force caused stress, and funnily enough, the direction of force and the direction of stress happens in the same direction. So when we talk about shear stress, you have positive and negative on the shear force diagram. The shear stress will go in the same direction as that using your positive sign convention. I'll talk about that, but you can also get the same thing by doing the interpretation of what I just said. So that's why getting those positives and negatives right was so important. Because if you get them right, it agrees with the physics. If you get them wrong, it doesn't. And so that becomes really confusing to people when you think a little bit more about it. All right, so we're going to have a try of that so that you guys can think about, which direction the torques are going in. It's a really simple little example. I want you to redraw what I've got and draw the stress vectors on it for me. Right, torque. Alright, so let's say I have, and I'm going to shadow out that bit, and I'm going to draw the back section hard, and I've got a torque on this end that goes like that, and I've got a obviously equal but opposite torque on this end that goes the other way, T. And I want my stress vectors on that front face. So what I'm going to do is draw some nice isometric boxes, or some crap isometric boxes, either way. Now you can draw them there, but what I like doing is actually blowing it out and making them larger so that it's easier to play with them. So we can do something like this. Oh, you can even shade the front face just to make sure that it stands out. See how once you shade the front face, it looks like it's on that plane that we've just cut. It makes it a bit easier to interpret. Don't shade it dark because you've got to put vectors on it in a second, but just a nice light shading will make it easier to understand. And then we reproduce. And what I would do is I would reproduce those front faces in the right place, in sort of, rough isometric, and then go back into the page, and it'll make it lay out nicely if you do it in that order. If you try to draw each cube independently, sometimes they get a bit messy and they get in the wrong place. All right, so I want you, I'll even write it. on the 4 elements. Alright, so feel free to use your mind, your fists, the cylinders that are in front of you. Orient whatever you're thinking in your 3D space, you orient it in the same direction as that, then you rotate it in the same direction as that, and then think about what's happening on those front faces and draw the vectors on. Draw the front face vectors, and then you can draw the ones back into the dimension. Alright, how did everyone go? Easy? Yeah? Anyone not 100% comfortable with that? Alright, does everyone's arrows point around in a circle? If you were to trace the arrow and go in the direction of the arrowhead, would you draw a circle, or would you end up drawing a backwards arrow somewhere? No? Good. So that's the check, right? So we're going around in that, so the fabric's going to be pushing down like that, and it's going around in a big circle, which means one that way, and then it comes around, that way, comes around, that way, comes around, that way. And I like drawing shears as a half arrow rather than a full arrow, because by the time you have axial loads and bending stress loads and all of this other stuff, it's much easier to interpret a couple of shears with half arrows and a couple of axial loads or axial stresses with full arrows. If you have full arrows for everything, it gets a little bit confusing. So it's just one of those conventions that'll make your life a little bit easier, particularly when you're in a hurry, because when you're in a hurry, everything gets, 50% messier. And if you have those conventions down, it'll make your life a little bit easier. So all we need to do now is add the additional ones. So as I was saying, shear always goes around in a plane or on 4 faces. So this back edge has to have a complementary shear like that. This top edge has to have a complementary shear like that. This front edge has to have a complementary shear like that. And this top edge has to have a complementary shear like that. And obviously each of these cubes have 2 more shears on the back faces that we can't see. If we were to draw them in 2D space, and I'll talk a little bit about that, but what you might end up with is something that looks like that. And probably no one can see that through the computer now. Sorry. Together, 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 like that, yeah? Alright, so that's torque. Any questions on that before we move on? Straightforward, everyone's done it before, just for a refresher, good. Alright, bending moment. Bending moment, again, we've done it to death. You should be pretty confident with what's going on. We can calculate our shear force and bending moment curves for any particular combination of forces. This one's one you may or may not seen. Have you seen this one? This one's called a pure bending test. And the reason it's pure bending is because if you have a reaction force, even forces down a reaction force, and they're relatively, well, they don't need to be evenly spaced, but that and that needs to be even. Then force goes up, force goes down, force goes down, force goes up. You have shear in the left bit, shear in the right bit, but in this center section you have pure bending. You have no shear, you have only bending. All right, and that's useful in some circumstances if you want to do tests on, bending stress and that kind of stuff. In this context, it just means that we have a bit of a funny looking bending moment diagram, but it's, you calculate the same way you calculate any bending moment diagram, just, calculate those sections, calculate some of the moments, and you're good. So, our bending moment diagram tells us what the value of M is. All right, and that value of M anywhere. Because if I find that I have maximum torsional stress in the center of this member, then this value of M is what's important. And maybe if I have a maximum value here of M, I'll check an element here and I'll check an element here and work out which one is the more critical. All right? So it's not just a matter of knowing what maximum M is. These curves give you M everywhere because you might be using more than one critical stress element, and that's very important. All right, so as we will know, once again, we have an equation for stress. In this case, it's a tensile stress, or a normal stress, more specifically. And the equation for bending stress is MC on I, M being the moment that we get from that diagram, C being the distance from the neutral axis, all right, or the neutral plane technically with bending moment. So if I'm bending something up like this, that's the distance, the perpendicular distance from the central plane, not from a central axis, from a central plane, all right? Which means, the reason that I say that is, and I think I've got a transverse shear example for us to do. If I have bending and forces in the horizontal plane, like this, so that this bends, let's say, that way. All right, you guys are all used to seeing this and you work in the vertical plane real easy, but as soon as I put forces on it this way and ask you to calculate the maximum bending stress, probably 50% of you will have a nervous breakdown. Basically, it's just a flipped plane, all right? And it doesn't matter, it's exactly the same, so long as you understand that the neutral plane that we're calculating C from is perpendicular to our force, or perpendicular to our mode of bending. So if it's a horizontal plane in the center, if I'm bending it this way, it's a vertical plane in the center if I'm bending it that way. All right? Simple enough. So you'll need to start getting pretty comfortable with dealing with 3D space rather than just the real simple 2D examples that you're probably familiar with. So that plane for a rectangular cross section, very easy, happens in the center. If you have a more complex shape, like let's say a triangle, it's going to happen in a different place. And you can get that from textbooks. Our textbook has a few examples of it. You can get it online. You can find it wherever you need. Triangle, I don't know for sure, but if I had to guess, I would think it would be 1/3 up the triangle in a plane, but you can confirm that yourself. But so that's one example where the neutral plane is really a plane at the centroid of the cross section. And that plane is perpendicular to the direction or the mode of bending. Okay? So that C is our vertical distance up, and because we have that linear relationship the same way we do for torque, at the central plane C equals 0, therefore stress equals 0, and the further we go away from the center, the larger C is and the larger our stress is. So that's why we have that sort of triangular cross section or triangular stress profile that you'll be familiar with because of that equation. Now once again, I is the moment of inertia. I've given you two examples in the bottom right there, I for a circular cross-section and I for a rectangular cross-section. One thing that, no matter how frequently I say this, people still get wrong on quizzes and exams. Look at the equation for J, for a circular cross-section, pi d to the 4 on 32. And I is pi d to the 4 on 64. And the number of times I see that used backwards and the wrong way around and someone used 32 where they should have used 64 and vice versa, make absolutely sure. For the exam for this subject, you get an equation sheet. And all the quizzes are open book. All right, so there's absolutely no excuse to screwing that up, especially now that I've flagged it in the terms that I have. So make sure that you get your I's and J's around the right way. Notice that that's d to the power of 4. Do not give me an r to the power of 4, or do not give me an r to the power of 4 divided by 4, because that only works when you just have squared, yeah? If you want to use r, then make sure that you understand algebra. Otherwise, convert it to d, please, okay? So make sure you get that right. It's really simple little screw-ups like that that'll carry on through your entire problem and ruin everything, okay? So attention to detail to the little stuff will make your life so much easier when you get a solution. Because otherwise you'll be getting solutions of, 100,000 gigapascals or something like that, and you'll realise you've gone really, really pear-shaped somewhere along the line. And then you'll have to find it frantically in a quiz, which is never fun. All right, so the one other thing, and once again, I've got some blocks up here, but I won't give them to you. You can visualise perfectly well with your hands. We got moments up, obviously we're bending, and you can see if I put a rubber band around the outside, stretching on the bottom, compressing on the top. Make sure you get your tensions and compressions right, because when we come to do stress elements, we have to draw them. And if I had, for example, an additional axial load on this that was in tension, it would be adding at the top and subtracting at the bottom, and if you get that backwards, you get it wrong. Fair enough? So you need to make sure you get your positives and negatives right. There's probably a way of aligning that with the bending moment diagram, but yeah, I'm not going to bother with that particular one. So it's just easier to visualize it and make sure you get it right physically. Okay, and then whatever the M value you get on the bending moment diagram, the magnitude is what you use for the M. So if you get a negative bending moment diagram, it technically just means that this is flipped around, so there'd be a positive sign convention that you could think about. Just make sure you get the physics right. If it's bending this way, you know it's tension on the bottom, you use a positive M and get tension, okay? And so for this example, our candidate stress element, if we go back to our bending moment diagram, bending moment's maximum on the left-hand end, and in the absence of any other stress, then our candidate stress elements we're going to put on the left-hand end there. And we'll put 3 just to talk about the fact that we've got 0 stress in the center and maximum on the top and bottom. Bottom in that case is compression and tension on the top. All right, and so that's the way I draw my stress elements. I calculate sigma based on MC on I, and then I would have calculated my stress element for that particular circumstance. Cool? And I've drawn in really dark, sort of a dark infinitesimally thin line at the top and a dark infinitesimally line at the bottom. That's the space where maximum bending moment occurs. All right, anywhere along that top edge or anywhere along that bottom edge in this particular circumstance is where maximum bending moment occurs. For the second example, where we have our force in the beam, once again, you'll recall the bending moment diagram looks like that. We have a maximum value at a single plane. And so that's throughout the length, our maximum's in the center. Throughout the cross section, our maximum's at the top and bottom. So once again, I have a single edge or line and a single edge or line where that's maximum. One's maximum positive, one's maximum negative. And so my stress elements once again look like that. In this case, if I have a force pushing down in the center, tension at the bottom, compression at the top. Yeah, so just a nice 3D visualization and get it right. This guy, think about the length. We have maximum throughout that entire central section and it's even. Yeah, so throughout that central section, M is even for more than just one section, it's for that entire volume. And then when we think about our maximum and minimum, we know maximum and minimum happens at the top and bottom surface. So now I have a maximum surface at the top and bottom, and arbitrarily I've just chosen my 3 elements in the center of that, but that doesn't necessarily need to be the case if you've got a different stress case that's going to add or subtract from it. And once again, forces up at the sides, forces down, so we can visualize that that's going to be bending down, so we've got tension on the bottom and compression on the top. And that's what I've drawn right there. Okay? Is everyone comfortable with those? Good. What do I got next? Transverse shear. All right, let's have a problem. All right, we can do this problem and then you guys can have a 5-minute break and we'll get through transverse shear after that. All right, bending. Alright, I have a nice circular cross section just to make you have to think about it a little bit. Force. Okay, L on 2. L on 2, and I'll even do an axis because we need to start doing that as frequently as possible. X, Y, Z. Alright, so draw all your diagrams. And A is max M. B where's the maximum bending stress? C. Draw the critical stress element, and all I want on that is the vectors and the direction of vectors for the bending stress. So that should be really straightforward. If you're listening to what I just said, you should be able to punch it out pretty quickly. Yeah. Alright, how we go? Everyone got a solution? Everyone most of the way towards a solution? I mean, this is the exact same thing we've done like 5 times already in terms of these guys. So F12, F12. And based on our coordinate system, that's X. And we should probably put our coordinates on the left here too. Let's give us X and Y. Right, so shear force, if we did our sections, we'd know that that was F12 till there, and it was negative F12 till there. And that our, let's say, shear force diagram, bending moment diagram, and our bending moment goes up to a max and down. And if you wanted to determine that max, what is that? FL on 4. Yep, so everyone got that? Easy enough? Right, so now the complicated bit is, where is our maximum M? Just next to where? L on 2, yeah, basically anywhere in that center section. So if I was to say, where's the maximum? I would say maximum M occurs anywhere in the center section, halfway along the beam, something like that. Any of that sort of wording, so long as I think you understand what you're talking about, you'll get the mark for. Alright, now, if I was to redraw my cylinder, making sure that I get my ISO looking pretty similar. Alright, so we've just said anywhere in this center section here as our maximum M. Y, X, Z. Alright, so where's our maximum stress? So actually, if I was to say something like that, A center plane at L on 2, something like that. Alright, B, where's our maximum bending stress? Top and bottom. At the very, very top and the very, very bottom. Is it a line? Is it a point? Is it a surface? Point? Yeah. There. And there. Top and bottom points in center at L on 2. Okay, so we have 2 singular points where that maximum will occur, and C is draw the critical stress element. So I'm going to draw the top and bottom one. One there, and one there. You draw one in the middle if you want to, but obviously it's 0. And just give myself some space. Remembering I draw the front faces first. With shade. And my back edges. Alright, top element, tension or compression? Compression, right. Compression. Bottom element is thus tension. And that's sigma. Oh, that's terrible isometric. Sorry about that. Okay. So compression stress, tension stress, and that equals, let's say, what do we calculate? FL on 4 times whatever C is on I. You can say something like that, or you can just say sigma. Obviously, we'll have values when we're actually calculating these things. All right, so is everyone comfortable doing that? Or mostly comfortable doing it? Yeah? Cool. All right, let's have a 5-minute break, and then we'll do some transverse shear and other little bits and pieces. All right, guys. Hopefully everyone's back. Mostly? Okay, so that's some of the simple ones. Transverse shear is what we're going to do now. Transverse shear, again, it's relatively simple. Some people seem to get a little bit tangled in it, so hopefully I'll try and give it as clear an explanation as I can, and then everyone can be on board. I've used my 3 examples from the bending stress, because as we all know, when you have transverse forces that cause bending stress, that also causes transverse shear. And so this is the same thing as before, except I've just added I've just used my shear force diagrams by themselves. Hopefully everyone's okay with actually getting those shear force diagrams from these particular free body diagrams. We've had enough practice by now. And so if I was to say, where is the maximum shear force in this first one, we know that it's everywhere. It's throughout the entire cross section. That's the shear force, not the shear stress. We'll talk about that. But the shear force is maximum and equal throughout the entire length of that member. In this member, we know that F12 minus F12, in magnitude terms, it's equal throughout the entire length as well. It's just that it's positive in one part of it and negative in the other part of it, which just means that our stress vectors are going to change direction. And in this particular example, as we talked about, in that central section, we don't have any of the shear force because just of the way the force balance laid out. And so we've got a positive shear force in the left and a negative shear force in the right, which means that this bit of volume and this bit of volume is where the maximum shear force occurs. All right, so that's the first kind of test. The first, all right, where's our maximum force? Now we need to think about, all right, what does the stress distribution look like throughout the cross section in any of those maximum areas? And in some circumstances, not the maximum areas as well. If you've got, lesser values, they might add up to a larger bending stress somewhere else. Yeah. So you need to be able to calculate the maximum stress anywhere, or the value of stress anywhere. But we'll look at the maximum for this example. All right, so what you're actually calculating on this previous diagram, this V, if I was to just do shear equals V on A, everyone's seen that equation, that's our standard shear equation. That assumes a perfectly even distribution of shear stress. So same at the top section and the bottom and the middle, throughout the entire cross section, even. Now, what that gives me in transverse shear terms is the average shear stress, but transverse shear doesn't evenly distribute throughout a cross section. Transverse shear actually looks like this. It's like a rounded profile. I'm not sure whether it's rounded, I think it's parabolic, but anyway. Have you guys done that actual profile and working through that profile in CS 2001? Just a tiny little bit. All right, so did you guys get a textbook for CS 2001? Did you guys buy that textbook for CS 2001? If it's anything like the textbook I had when I did that subject, it's really good. And there's an entire chapter on how you calculate those shear profiles. Because as soon as you're not doing a rectangle, if you've got an I-beam or something like that, this parabolic profile gets really complicated and messed up. All right. So if you're interested in knowing what the values are throughout the entire cross section, that textbook, assuming it has a chapter like that, is a very good reference. Now we don't need to do it in this subject too much, but that's further reading if this stuff's a bit confusing to you. Okay. Please let me know if that textbook doesn't have a chapter like that, and I'll photocopy my chapter and PDF it to you. Okay. Now, this circular section happens, this is the bit that gets a bit confusing for some people. We know that a shear element, if I have, let's say I have shear on this element like this, like so, and that's the sort of front face. Now, I've got material over here to be actually applying that shear stress to the front face. Is there anything on the top edge of that beam to apply shear stress or to apply shear force? There's nothing. And so if I've got nothing to apply shear stress at the top face, that means this top face of shear has to be 0. And what we know about shear is that whatever the shear on this face is, this face has to have exactly the same value of that. And this face, and this face. So we know that for transverse shear, because it goes around in a circle like this, because it's in plane, at the very top edge, that stress has to be 0. Same story at the very bottom edge. So hopefully you understand that this is our beam, and we've got our forces wherever we've got our forces, one down on the end up there. Top and bottom edge, because the outside surface cannot transmit, carry, have any transverse shear on it, it means that the front face at that point can't have any transverse shear on it, 0. But as you get more and more into the material, you've got more material to actually impart that transverse shear on the top face and carry that transverse shear on the top face. So that's why the distribution changes throughout the cross section. All right? And it changes. It sort of increases until it gets to a maximum, and it comes back down to 0. And so that's why you have that sort of parabolic face, because we know it has to be 0 at the top and bottom, and the further away from the top and bottom we get, the more the magnitude actually is. Now, if I was to take all of those values and take an average, that's what we get. All right, so the average of that, if I drew that like this, and I was to take an average or find the centroid of that shape or whatever, somewhere like that, then that is V on A. So if I calculate V on A, that does not tell me my maximum. If I use V on A as my shear stress magnitude determination, I'm going to have a maximum shear stress greater than what I've calculated. Chances are stuff will break, you'll get sued. All right, so we need to use the real maximum. And that just comes from like geometry and, that chapter of the textbook that I was talking about. You can calculate it if you have a dicey geometry. So in this class, you'll be dealing with rectangles and circles mainly. But as an engineer, you'll be dealing with whatever the hell the design you've come up with or someone else has come up with. So you need to be able to understand that this is what we do for this, and then find the resources to be able to do the same thing for whatever case you have as a practicing engineer. All right, so that's why I pointed you to that textbook, because if the equations that I give you don't count, doesn't mean there aren't equations for it, just means you have to work them out yourself. All right, so that's the tools we're trying to give you. So for a rectangular cross section, the maximum at that center point is 3 on 2 V on A. Very easy, just 150%. All right? And for a circular cross section, once again, it happens at the center plane, it's just 4 on 3 V on A. Okay? And so what we actually use when we calculate our maximum is those equations, depending on whether we have a rectangular or a circular cross section. And if you have a different cross section, then either look it up in a textbook, look it up online, or calculate it yourself. Or I might give it to you. If it's an exam, I'll give it to you, but generally we won't deal with complex geometries like that. All right. Now, that maximum occurs once again at that neutral plane. And so if we're talking about forces up and down, the neutral plane's in a horizontal. If we're talking about forces in and out, that neutral plane's at a vertical, and any combination thereof. Right? So get confident with what that is. Anywhere along that plane there, I could get my stress element. Anywhere along the top and bottom, I'll have a 0 stress element. And anywhere in between those things will be some combination of both. But almost always that won't be a critical place. You'll either have a critical in the middle or critical in the top and bottom, depending on bending and torsion and that sort of stuff. Now this guy, once again, the entire center plane. So it's not just the center of the circle, it's the entire center plane is where that maximum occurs. And so that might be on the left-hand side, it might be on the right-hand side, or it might be in the center. Top and bottom, in this point, for a circle, top and bottom is a point. And at that point, you have 0 transverse shear. Okay? So if I wanted to work out where my transverse shear was, I'd do those type of stress elements and then work out what the other combinations of stress are and work out which ones add and subtract and all that kind of stuff. All right, so those same three examples that we talked about. So remember, we've got, the first one we had V even everywhere. Now we know that for that rectangular cross section, the maximum, if we use that 3:2 V on A, is anywhere in the center plane, anywhere in that neutral plane. All right, so I can take a critical element anywhere on that plane. If my bending stress is maximum here, I know that's top and bottom and 0 in the center, but if I want a candidate element to match up with the maximum stress from any other type of loading, I can know that in the center plane, that's my maximum, sigma max. Now, before I get into the other two, let's have a bit of a look. My shear from my shear force diagram, is it positive or negative? Positive. And let's think about our positive sign convention. What do the vectors look like on the front face of an element with the positive sign convention? Positive is down. Look at the direction of my shear. Down. Yeah? Now look at this one. Remember that we have positive to the, let's say, left and negative to the right. Once again, I've got my maximum at that center plane because we know the maximum magnitude is the entire length. The maximum throughout the vertical cross section is at the center plane. So my maximum's anywhere at that center plane. But if I take elements on my left, it's positive shear, down. If I take elements on my right, it's negative shear, up. All right, so I can use, if I get the shear force diagrams right, I can use that to get my stress vectors right. I can also use the physical interpretation, like what I was showing you before. You can use your cylinders, you can use your rectangles. Once again, exactly the same. That fabric we were talking about on either face. Let's say on this one I've got my force down and my force up. So this one just has a force up. So I'm dealing with this side now. So this is just force up, this is force down. So this one's going to go up. This one's going to go down, right? This one, if I don't have any forces balanced on it at all, it's just going to go up. So if I do my physical interpretation of that going up, what direction is the fabric on this face going? Down. If I look at my vector, down. And if I did it over to the right there, so now I only have a force up and I have my force down on this one. This one's now going up. And look at my front face, as that go up, what direction is the vector going? Up, right? So if you get this stuff right, the sign convention stuff right, it all agrees. Right? You've got multiple different ways of confirming that you've got the vectors right and everything, because it's physics. There's only one way this can happen. There's only one way it happens in reality. So ideally our analysis technique should mirror that, and every single different analysis technique we use should give one solution. And if they do, then you understand how to maybe get, you calculate it one way and then you confirm it the other way in an exam and make sure you got the answer right. Yeah, so engineering is all about checks and balances and trying a couple of different ways to make sure we haven't screwed it up. So there's a few different ways you can confirm this stuff. Our last example, once again, we knew the left-hand end had max and the right-hand end had max anywhere in the center plane, because we know this is, we've got a circular cross-section now, but it doesn't change, it's still that center neutral plane. And on the left-hand side, we had positives, and the right-hand side, we had negatives, and so we draw our shears accordingly. Cool? Make sense? Easy enough? Great. Let's do an example. Alright, so basically I want you to draw me a stress element on this side of the force and a stress element on that side of the force where that shear stress is greatest, and that includes the directions of the shear stress vectors. Now, probably good exercise to discuss, how would you draw a shear force diagram for this? So on the XZ plane, and you just stand it up like that, yeah? Yeah. So if you start interpreting this stuff as just being 3D interpretation, think of SolidWorks, you just flip it around, yeah? It still exists, it still works, you just flip it in a particular direction. So this one, it's sitting down like that. If I was to sit it up straight, this is where drawing your axes is really critical, because if I now draw my axes, probably can't see that. Let's say I'm drawing a shear and I draw my X there and my Z, and I actually label them X and Z, did a free body diagram, shear force diagram and so forth. That would work perfectly, and I'm back in my standard 2D plane that I like working in. The only thing will be is once you've got that value, you need to be able to look at your shear force diagram, treat it like a three-dimensional space and lay it back down to the way it needs to go if you want to do that positive and negative thing and get it right. Otherwise, you can just get your blocks and you can go, all right, I've got a force in the middle that does that. What direction do my vectors go on? You can actually do the interpretation in 3D space yourself without the shear force diagram. Up to you. Try both ways. It's good to have two different ways to do something. All right, so everyone's had a bit of a go. You've had a bit of a think. Some of you seem like you know what you're doing. Some of you most of the way there. Shear force diagram, bending moment diagram, free body diagram. Honestly, with this stuff, just do it as second nature. Like from a mechanistic standpoint, you just do it and you understand it and you get it right every time. Then you can use it or you can not use it. But it's sort of the first step in analysing almost anything that we do. Just do it as a second nature kind of thing. I actually didn't mean to do the bending moment diagram because we don't need it. We're talking about shear, and I just did it automatically. Because if you get that into your procedure, you just do it. Now, where's our neutral plane in this particular image? Yep, so the YX plane in the center, exactly. So if I was to draw that, I'll call that plane. Something along the lines of that. You can even give it some of those ones. All right, so we know that our shear stress is going to be maximum at that center plane. Where is our shear stress going to be 0? Front face and the back face that's sort of in behind there. So if, based on the sort of convention that we've been doing, if I was going to do 3 boxes, I might do box, 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 something like that, yeah? So like that, one on the top and bottom where it's 0, one in the middle where it's maximum. And the reason that I'm talking about those 3 is because if I was talking about bending moment, then bending moment's maximum top and bottom and 0 in the center. And when we start combining them, we'll need to be thinking about that. All right, so we'll talk about that when we combine them. But let's say that we're doing 3 boxes. Really, the center one is the one that we're most interested in, and that's the one that we need to get the shear stresses right for. All right. Now, in the absence of the ability to show you 3D stuff in your mind, Z, X, that's how our shear force diagram translates down onto space that matches our diagram. Hopefully. Yes. Yeah? So, you moved it up to get your shear force diagram. Now, the reason I'm drawing this is so that we can relate that to our positives and negatives. In your mind, hopefully you don't need to draw it, you can look at your shear force diagram and use your hands in the air if you need to, lay it down flat, that matches that, and think about positives and negatives. Remembering that Z positive is that way, so our positive sign convention needs to be oriented the same way. So if that's up, then a positive shear would be down, right? And a negative shear would be up. So, if I was to redraw my elements in the configuration that we're talking about, positive, with that being up, that means down is this way, and that matches that. And negative, that being up, means up is negative. Yeah, so you see why I'm talking about 3D spatial kind of thinking. You need to be able to think about these things in space. You need to be able to use your 3 X, Y, and Z axes, your Cartesian coordinates, to define where up is to you, because that positive sign convention only works if up is up on the sign convention. Yeah? And when you're in 3D space, that gets a bit confusing. Now, if that's the way we've drawn these, that's what our shear force diagram is telling us we need to do. Does that make sense? Hopefully it does, because I just did that on the fly then. Does that make sense with our actual methodology? So let's say we're doing this one's going that way, looking at the fabric, that front face, the vector goes that way into the page. Correct. If I'm looking at this one goes that way, this force comes down, and that front face goes out of the page. Alright, so I can use the shear force diagram way, I can use the physical interpretation way. Ideally I use both ways, and they both say the same thing. Okay. Now, is everyone at least 50% confident with that? Right? I highly recommend you guys have a couple of goes at that over the next couple of days. Have a go at all of these. You can make your own problems up. Hopefully you remember the sort of study techniques that I was talking about, where you don't just do the problems I give you, you come up with your own problems. Alright, so with a bar like that, in this plane, you don't need force, force, force. You can have 5 forces. Put 5 forces on it, make sure they balance, so sum of the forces equals whatever, equals 0. Put 5 forces on it, do this, and give me a shear stress element at, the division between each of those forces. That's a really good study problem. And it'll make you think, and if you do it between a couple of you, you can, if everyone gets the same answer, you know it's right. If everyone gets a different answer, you can talk about it, work out why one way is right or one way is wrong. If you're still confused, come and talk to me about it, but regardless, you've thought about the problem, you've practiced it, and it's something that I haven't had to give you that you can study and actually get a lot out of, okay? So I recommend that you do that, set up a couple of these different problems for yourself and actually have a go. Now, I think I have 2 or 3 slides left, and then we'll be done. Oops. Okay. All right. So that's good. All right. So we've talked about axial stress. We have talked about torsional stress. We've talked about bending stress, and we've talked about transverse shear. Now, this last one, direct shear, is one that you're probably not going to have too much to do with, aside from maybe when we talk about bolts. It's an example where you know where that transverse shear is carried throughout the entire cross section? This is where the actual geometry of whatever componentry you're doing isolates the shear to a single plane. All right, and so this yoke is a good example where hopefully that's a two-dimensional drawing, but you can understand that the left-hand bit of the yoke's like that, and the right-hand bits of the yoke's like that, and it's got a hole through it and a pin that goes through that centre. All right, and so the fact that if there's small tolerances on that gap and that gap, that force P is being carried by that pin just on that singular plane there and that singular plane there. All right, it's not being distributed over any particular distance. The stuff that I was talking about shear being unevenly distributed throughout a cross section is less a case for direct shear, because if this is all small tolerances, you actually do have material on the outside there, so it doesn't actually have that same profile. Generally, we just assume that it's evenly distributed with direct shear because of all, the assumption of tight tolerances means that all of it's distributed right through that center section. And simply enough, the way we calculate it is P on A. Even distribution, P on A, whatever that area is. Now, if I have two sections that I'm calculating, technically the force for this one is going to be half P, and the force for this one is going to be half P, and the area is going to be whatever the area of the pin is. And that's going to be the stress in that cross-section of the pin. Hopefully you don't have any other modes of stress, so that's a pretty simple problem to analyse. You calculate your stress, and then you compare it to some failure criterion, and you're good. And if we have fatigue, then there's a few more steps that we do that I'll teach you, but once again, it's very simplistic. The other thing is that it's not just that pin that will have that shear stress applied to it, because obviously the pin is imparting force back on the yoke, and so there's parts of the yoke that will have that stress, and the same goes for anything where you put a bolt through a hole and you actually put tensile load on that bolt, or shear load. You have singular shear. You guys know what single shear on a bolt is? Bolt, pin, anything like that. All right, single shear very simply just means that single shear means you have a single shear plane on the bolt. Double shear means, like that yoke, bolt, that you have two shear planes. Which one's better for the bolt? Double. Yeah. Every single day of the week, double shear is better than single shear. For the same loading, definitely, because you've got all of that 1P divided by that area, whereas here you've got half P divided by the same area. So that's why for the FSAE competition, for example, most of the bolts that you do for suspension components, unless you've done really good analysis on them, need to be in double shear because it's much safer for the bolt. The other thing with single shear, think about bending. All right, so it's not just shear that we're dealing with here now. If you have uneven asymmetric loading on a bolt, pin, or any other thing, this thing is now starting to tilt like that. And it's got sort of oblique loading and potentially tensile load as well as that shear, and everything's going very poorly for the bolt. All right, so that starts to become a much more complicated case, and if you only analyse it for the direct shear there, you might be missing half the story. Whereas with double shear, it keeps it nice and even, and those other types of stress are far less likely unless you've got poor tolerances on your gaps and things, at which point then, less so. All right, so that's a kind of a sidetrack, but that's what double shear is. And so we were talking about this yoke, and this yoke is basically where the pin's trying to pull itself out of the yoke, or out of the plate, or out of the, whatever you're pinning, bolting, etc. And so if we look at one of these end sections, that's the pin, or maybe the central section here, I think this is. So the pin goes through the center of it. We've got shear on each end of the pin, but then that pin wants to pull itself out of the yoke. And so those two planes, the plane at the top and bottom, is basically, if you imagine that this was a really, really soft, potentially almost brittle material, you yank that pin, that's the bit of material that will get torn out when you pull the pin. Yeah, and so those two planes that are defined by the top and the bottom of the pin, bolt, or whatever it is, are the actual direct shear planes. And once again, P on A, where A is the total area and P is the force. And that's roughly what we analyse that for. And generally a good rule is to see this dimension. So generally from the top of that to the outside edge is at least the diameter of your pin. You want at least the diameter of the pin in that dimension, possibly maybe 150% of your diameter there. But you'd analyse it, but that's the starting point. You wouldn't ever have a really, really narrow section because you'll tear the bolt straight out, and there's plenty of examples in that in machine failure. Cool. All right, so that's direct shear. Just so you're across it, we're not going to do a lot in this class about it because it's so simple and there's really not much more than just P on A that you're going to be calculating. But whenever you analyse an actual machine component, that's what you come back to if you've got a pin or bolt or something that needs to stay in there. Now, last two slides. First one. Obviously, we can analyse all of these stresses independently or individually. Hopefully you're relatively comfortable with that. If you've done it in CS 2001, which you have, even if you don't remember, you can refresh it. Easy enough. What we're going to do in tomorrow's lecture and the tutorial on Monday is combine them, all right? And the way that we combine them is that, fortunately enough, with stresses, we can analyse them individually and then we just add these stress elements together. So if you have bending and transverse shear and torque and axial all at the same time, you can analyse all four of those loading mechanisms separately and then bring the stress elements together and add the vectors. All right? Add, subtract, whatever. All right? And so that makes it really easy to analyse. We just analyse the simple stuff and bring them together. It's just complicated as to where you might choose those candidate stress elements based on what you know, and so that becomes a bit of engineering judgment. Now the challenge is you get situations like this. I've got tensile stress just on this one, and shear stress just on this one, and tensile stress just on this one, and maybe I have, shear stresses added together and subtracting and tensile stresses. Which one's the most critical? All right. And so which one's the most critical? We need to work out principal stresses. Or we work out what's called von Mises stress, which is an equivalent stress, which is actually what most of the time we use as engineers. But what we need to do is calculate a stress that is representative of a maximum. So principal stress, let's say principal normal stress, that would be that already. This shear one, you'd have to rotate around to a 45-degree plane or something to get what its principal stress is. Then you compare this one's principal stress to that one, and the maximum one's the one you use. Whereas von Mises doesn't require any of that rotation. You just calculate one stress that's representative of the full 3D stress state, and that's what you use as your comparative mark. All right, but we'll do that. But what I wanted to flag here is that as we're combining them, it's not just a matter of calculating all these vectors. At some point, we're going to condense them down to a single number that we compare to our failure criteria, and that's what tells us whether it's failed or not. All right, and the last, and hopefully you guys are across this, is the idea that if we only have stresses in two planes, then we can represent it as a 2D stress element. If we have stresses in three planes, as in, so this face, top face, back face, bottom face, that's 2D. That's technically only 4 faces of the 6. If I have more stresses on this face or stresses on this face in this direction, that's a full 3D stress state. All right, so if I was to draw my axis, X, Y, and Z, I have X stresses, X stress, X stress, X stress, and one on the bottom, X stress, and I have Z stresses, Z stress, Z stress, but I have no Y, so it's 2D. All right. If I had anything in the Y direction, then that would be 3D, and I can't, in that case, condense it down to one of these representations. But almost everything that we deal with in this class, we'll be able to boil it down into a 2D representation. Now, the important point here is 3D Cartesian coordinate system, 2D Cartesian coordinate system that matches it. I've rotated it down to my 2D space. Once I calculate these, I might actually need to transpose this back onto the machine component drawing so that I know where the failure is going to occur, perhaps on what plane. So you need to keep that, and then you need to be able to physically interpret that back onto the plane. All right, so it's once again that 3D rotation in your mind that will become quite important. This is the interpretation of it, so we draw it like that, but technically what it is on the infinitesimal element is perfectly distributed on that front face. Okay? So don't go drawing vectors along edges or anything. It's in the center of that face. In the center of that face represents a distribution across everything. If you start drawing vectors on edges, then it gets very confusing what you mean. So always centralize, and then when you go to 2D, always draw them like that. All right, and we'll have plenty of practice on that. We'll go through a complete review of more circles, and we'll be doing a lot of that stuff as well. Okay, if there's no questions, that's everything I'll offer you. I'll see you guys tomorrow.